Startups are fun. Who's done a startup? Anyone?
An Intel startup.
Intel startup?
I did the big data centers.
Oh, okay, okay. Your startup was? Okay. So yeah, startups can be fun. I had one successful. Haven't had a mortgage since I was in my 20s, but I can't afford the island, so it's not the real startup. Had one where I showed up one day and the police tape was on the building, the door saying "Don't cross." Yeah, that was one of those kind of startups. The CEO was dragged out in handcuffs, and CFO, and
Oh dear.
but
Oh dear. Okay, there's Grant. So we'll go ahead and get started. Oh, there's Tom.
just take the box.
Oh, he is going to take the box.
The small box.
Okay, so this is our last class. We are going to have a test, but I'm going to steal some time. As I said in my email to you, we are interviewing for a new faculty member next year. I'm just thinking, since both Fawn and I are transfers from Klamath, so we haven't had a hire in our Portland area for like 17 years. We haven't had to interview someone for a faculty position since Jay. I think Jay was with us for like 16 or 17 years before he retired. So this is a big deal for us. And one of the things that's always been, I think we felt very strongly about, is getting the students involved in the interviewing process, you know. And so you guys can get, you know, give the thumb up or, okay.
No tomatoes out there.
Don't,
Good.
don't
No,
throw
we just have
anything.
pieces of pizza.
Yeah, don't throw anything. So, so Dr. Edward Riley, and one of his specialties is actually operating systems, although today I learned that he knows compilers quite a bit too. I should have him speak something about compilers rather than operating
We should have
systems. But
crossed over.
we should
but
have, yeah, we should cross over or.
that,
So,
that last part that
Yeah.
hopefully you can get enough students to take the third part of the course.
yeah. So we're having to offer the advanced compilers class for as long as I've been here, so.
So should we do
we'll
a
see.
poll now before or after the test?
Oh, I don't know. Okay, so I'll just turn it over to you and then, it has about 45 minutes.
Okay.
Okay, all right.
So my name's Ed Riley, originally from the Boston area,
Thank you.
and went to college at UMass out in Lowell, Mass. Got a PhD there and a bunch of other degrees. I started life as an engineer and then got into computers. So I do a lot of mechanical stuff, did robotics, factory automation. Got into computers, did elevators for a while. That was fun. Business went through the roof. Well, the counterweight's heavier than the car, so they do crash up, actually. Now you should be nervous. I walked the stairs for less than 10 stories, so that should tell you something. And then I did a variety of startup companies, as I was saying. Some were successful, some weren't. A lot of fun. You get to do a lot of things like work 100-hour weeks and work hard and own part of the company. It's a great experience. Everyone should do it at least once. And then go off and work for a huge company like Intel, which I did once, but it was a 15-year stint. So in Intel years, I was there 2 sabbaticals. If anyone follows that like dog years. So I was ready to leave. My last job was with the CPU team. I was there for about 10 years. Everything from the architecture side. So I worked on the simulation environments for the new chips and the new features to helping the designers build tools. Yes.
Did you work with Bob Martell in the CPU area? He was my boss. I wonder if you.
Yeah.
know.
Bob is familiar, so I think we were in the same building at the same time.
Cool.
I didn't work closely with him. There's 17,000 employees and probably another 20,000 ex-employees.
Right.
But it's a small enough world, you're running the same people over and over again. My last job for the last 7 years was with the manufacturing team. So we got their brand new chip designs and I helped automate the factories to mass produce these things and test them. Like the i3s and i5s, i7s. So the i3s popped out, 7 years ago, and they got popular. We were selling making 2.5 million a week for something like 8 months. So I had to get a lot of equipment in place and be able to turn it in and out from different product lines. And so lots of automation, lots of software automation. lots of ways of figuring out how do I push this button and then push this button 2 weeks later and everything still worked the same. So if you're good at making buttons, make the easy button. That's your job in life. Make the easy button for everyone else.
George.
There you go. All right. So tonight I'm going to talk a little bit about operating systems and specifically threads. There we go. All right. So I have a little bit of an objective, giving you a brief overview of this. Then we talk about some threads. I realized that if you haven't had operating systems and processes, I need to cover just a little bit there. Then we'll talk about threaded applications, and then threads versus processes. How are they different? Why are they different? Thread performance, always an issue. And then I'll get into a little bit of code. I wasn't sure if I had a live server. I just did a few slides, Foilware, and then we'll wrap it up. All right, so my objective tonight is to introduce you to the concept of threads. How many people have done some thread programming, any Java? I see most of the hands going up. Okay, C, Unix, Linux, Windows. That's good. Okay, I'll give you an overview of processes, real thin overview of processes. And then we'll talk about the relationship between processes and threads. Next, we'll discuss some applications of threads, and then we'll examine the performance of threads. So there's a couple things you want to look at when we talk about thread performance. And then finally, give a little threads programming introduction. All right, so thread overview. Thread is basically an execution unit on a processor. It's the minimum execution unit. When we talk about processes, they tend to be larger, but thread is a small execution unit. So it could be a lot of different things, but typically you have snippets of code, and when you look at a program, they essentially look like snippets of code. Typically a function or a method if you're in an object-oriented world. A thread has a parent, and the parent is the process, so there's part of that relationship. A process can have multiple threads, but it doesn't have to. A process can be considered a single thread unit. Thread is typically executed on a separate core. So when we talk about cores, how many people have multiple cores in their computers at home? 2. How many have 4? 6? Westmere, that's one of my products. 6 cores from Intel with hyperthreading enabled. So 12 virtual processors. So you can run 12 parallel threads. A lot of it pegged at 0 if you're not doing much. So Intel hyperthreading is a partial core. I don't know if any of you knew that or not, maybe the folks at Intel. So it's not a full core, and I'll talk about why that is. But it acts like one, and to the operating system, it looks like one. So it'll schedule a process on it, or it'll schedule threads on it. And then we have simultaneous multi-threading, SMT, execute multiple threads in parallel, which is really what you want your threading for. So we talk about concurrent versus parallel. How many people know the difference between concurrent and parallel? Few. So you can think about processes running concurrently. And over some time, at that point, process 0 is running. Process 1 is not running at all. Then process 1 running, and then process 0 again. So it's the operating system that's doing this, and it's switching between processes. You don't typically see the difference. You don't notice it, but there's some overhead there, whether it's microseconds. Now in the thread world, the threads are truly running in parallel. They're running all the time through that entire time period. So concurrent appears to be running in parallel, but isn't truly parallel. So if process 0 and process 1 need to exchange data, one will stop, exchange data, the other will have to synchronize, versus in the thread world, they can have live exchanges of data. And I'll show what some of those look like. All right, quick review of processes. So process has a block of memory allocated to it. And typically you'll have code or text, as the author of the book calls it, then a data block heap. Your heap tends to grow up. Your stack is at the top, your stack grows down. You've covered that in compilers, how to generate pushes and pops and function calls and so on.
Of any languages, yeah.
In many languages. Okay. And process has a state, and you can think of the state as the execution phase of the process. So we start off with the process being new, it gets assembled, the code gets read off the hard disk, gets resources allocated to it, it gets admitted into the ready queue. The queue could be priority queue, it could be any other kind of queue. At some point, that process gets scheduled to run. The dispatcher runs it. It'll run for some amount of time, and then it may have its quantum expire, in which case it gets taken off the run list and pushed back in the ready queue, or it could complete and get terminated. And the third choice for a running process is to go to the waiting queue if there's some kind of I/O or other process support necessary. Could be synchronization with another process. A process also has something called a PCB, the process control block, and you can think of that as the state of the process. So yes, we have the state that we just looked at, and it has a process number, typically called a PID in the Unix world. If you do a PS-A or something, program counter, or could be called an instruction pointer, depending upon the text you're using, and then a block of registers. The registers are typically all the registers in the CPU that are needed to start the process again, exactly where it left off last time. In the Intel world now, you have the 16 processors, starting with the traditional AX or RBX. And you have the MMS, MMX, SMM, floating point, and then you have some flags and state processors. You also have, we talk about memory limits, but there's actually memory tables. So there's a fair amount that goes into this. Could be easily well over a couple of K of memory space. But the threads, on the other hand, the code for thread is contained within the executable file, just like it was for the process. It gets loaded when the process gets loaded, and it's part of the process. Then the threads can access and share resources with each other, but they do it through the data and through the heap. So in the case of the data segment or the data region, there could be global variables and multiple threads are accessing. From the standpoint of objects and object-oriented information hiding and so on, all that's maintained in the code, yet separate threads get access to the data at the same time. Okay. The threads can execute independently of each other. So thread 0 and thread 1, once they're started, they can run. Or they can be synchronized. So if you need them synchronized, they're synchronized. You need to be careful about simultaneous access to memory locations. If one thread is modifying a location and another's trying to read it, will it get an incomplete version of the data if it's a complex data structure? And we could talk about other mechanisms for maintaining that mutual exclusion, to make sure only one thread gets that data at a time. Threads run until they're blocked or terminated. So a thread context switch, and we'll look at what that looks like in a second, is it's much simpler when compared to a process. So in the process world, the process control block needs to get updated every time. So the OS writes this out into memory. The memory may need to go out to hard disk. Also this process space, and this could be megabytes or gigabyte. Think about a database in memory. All that might need to get written out to the hard disk when a process gets swapped. Hopefully you're not swapping your database. All right, so if threads run on hardware, is there any advantage of having more threads than hardware? Whoever has the Westmere with the 6 cores and the 12 threads, is there any advantage to having a 13-thread process, and why? Well, what happens when one of your don't have it?
I was just thinking about the question. Like, I mean, like, I know we used to have video games that would have like sound playing at the same time. You do your sprites, animation, stuff like that. So you have multiple threads going.
Right.
So that, but they only had one CPU, so at that point you would have to do it. So you wanted to have multiple things happening. So I suppose if you had a really complex program, you might want to have more threads than processors.
Certainly, because not all the threads are running at all the times.
Yeah.
You can certainly have a thread that gets blocked. It needs some data from somewhere. It's waiting for input from the user, the joystick, the rudder,
Yeah, exactly.
or the next batch of images off the hard disk for the next scene as you're turning around the corner
Exactly.
before the monsters come and get you.
Yeah.
That's what you're talking about.
Yeah, something like that. That's
Right.
the background threads.
Or opponents, I guess we have opponents. Yeah, so certainly having more threads is fine. Having way more threads than the number of processing cores is fine. It just starts to get a little bit less efficient than if you have the exact match. All right, so here's where we show the difference between the process space and the thread space. So in your process space, we said we have the code, the data, the files. The files are heap, stack, and register, and really just a single thread. In a multi-threaded process, you can have as many threads as you can fit into memory, but notice the top line, code, data, and files, those are shared. So there's one set of that. So if you have a thread that terminates, you have a small amount of memory that you have to recover and reuse. But you do have the registers, and each thread does have its own stack. And the thread has a stack. Why does the thread have a stack?
Because that's how it knows where that's how it keeps track of everything. It's execution.
That's executing within its block of code.
Yeah, exactly.
Exactly. So, and similar for the registers. It's modifying those registers as it goes through the code. So having that set of registers so that it can correctly save and restore that thread, similar to what a process goes through. So on the Intel hyperthread feature, it's not a full core, it's a partial core. And what it has is, it has a whole separate set of registers, but it reuses all the ALUs and the integer and the floating point and the MMX and the other units. So when one thread is not using all of those, the second thread can be using some of them. Hence, if you look at the performance numbers for hyperthreading, it started out around 30%, and then now it's up to around 60%. So a core with hyperthreading, excuse me, is equal to about 1.6 cores now. All right, threaded applications. So who writes software? Who plays with software? Okay. So what are some of the applications for threats? We heard one already, a game.
Yeah.
So take a couple minutes, meet with one of your neighbors, come up with some applications, maybe something you've used. What are the threads that are in it? What are some of the, what's the class of application?
I think if you rewind,
where you're at, processing multiple threads, and then all of those.
So the application, like, it's
When they go back to the evidence, they got one progress bar, upload that.
it frees up.
I guess the way I choose.
There's still a thing where. Well, there's no, what it comes down to is, where the thread. You have to update the progress bar. But you're on thread, and you have something to get back to the thread. I don't know why you do that. Yeah, you see sharp, yeah, you cannot touch the element and you show on the thread. Oh. So, yeah. That's another reason to get. Well, even if you just- if you- yeah, well, like, it's still good. It's still good. There's a. Right. It was just.
Everyone come up with some applications that you think are threaded. Okay, so we heard of games. What aspect of games do you think are threaded? How many people came up with games? Games are popular, right? So what aspects of games need to be threaded or could be threaded?
Any sort of IO activity like disk or
Yeah.
playing sound or anything like that.
I blinked, it's
gone.
okay. Why do IO and the disk activities in a separate thread?
So it'll keep running smoothly.
Okay.
While it's loading.
They take a lot of time. And if you're waiting for something to come back from the disk, then the rest of your program isn't running.
Right.
Yeah.
So you can avoid delays by putting some of these compute pieces into separate threads. Certainly disk access. How fast is the disk these days?
Yeah.
10 milliseconds. Even SSD is way less than that. How fast is the processor? 3 gigahertz. Yeah. Orders of magnitude difference there, even with caching schemes. Sound, audio, why would you want to put that in a separate thread?
Same reason, because it has to keep putting stuff into a buffer, so it's a continuous operation.
And what happens if you don't do that?
Then your program is going to have tiny hiccups every few hundred milliseconds as it.
What's that?
It's very jarring.
Yeah.
Jarring. Certainly you get that glitches in the gaps. How many people have IP phones? Who's happy with the service? Anyways, there's a reason that. What else? What else would be a good thing to put?
Video.
Certainly video. And why video?
Well, a lot of it can be vectorized for the city,
Okay. And
and that
What-
would make it more efficient to be threaded.
okay. Yeah, certainly vectorized. So what are some of the schemes for vectorizing video? anyone look at that in computer graphics. So you can certainly do things in blocks or in regions. You can even do it on scan lines if you wanted. So there's lots of different schemes to vectorize and overlay your objects, what's interfering, what needs to get removed. There's lots of schemes. And the more threads you have running, the faster you can get through that. You may even want to take your screen and partition it into little chunks. If you have a 256 core video processor, you can chunk your whole your screen into those pieces. There was another hand up, yes.
You have a networking system. So that you can queue stuff up to be sent out, or you can have a waiting thread to listen.
You don't like to think you're the master of the world and then find out you were the first one killed when everyone else's network updates yours.
Well, I mean, would you rather refresh a web page to see something happen, or would you rather just the web page show it to you?
Well, certainly there.
One way to think about it.
So that's kind of games, and there's some other things, fun things you can do in games. All your opponents could be in separate threads, so you can delete them and new ones can pop up. Your artificial intelligence, you can put that in a thread. That way it can be running and looking at the next scenes that are getting loaded and everything else that's in the buffer coming up. It can already be working out schemes to have fun with you before you even get there. Okay, what other applications can be threaded?
Kind of goes on the same line of games, but any GUI event or user interaction with the GUI, such as a mouse click or a keyboard press, all comes down on its own thread.
Mouse, I/O, joysticks, rudders, whatever you want. Wands, I guess they call them. Remotes. Okay. You can't just swish and have something happen. Certainly. So all your I/O you want running in separate threads. It's a low bandwidth operation, but you want it to keep running.
Sure.
Otherwise, it gets choppy. In the old days, you type ahead, and then you'd see your text catch up. You type ahead,
Or freeze altogether.
or freeze altogether. Right?
I've done a lot of utilities that way. We'll do a lot of number crunching in the background. You don't put them in a separate thread, then the whole GUI freezes. The person thinks your system crashed.
So certainly process issues in and out of the application. What else? What other applications?
Scientific algorithms and workbooks. I guess I had one teacher talk about they would do like calculate like a forest fire and maybe simulate it off some processes. And then they would just produce the data for like national agency or whatever.
So a lot of the early multi-core computers were originally built as number crunchers, just to be able to do vectorization and so on. So certainly you can have multiple threads. How would you reduce a problem to threads? Say you have a great idea, you can recreate the best weather predicting software for the whole country. How would you use threads to do that?
I guess you have to kind of collect data for all the different portions of the country and then make a decision based on that data.
Right, but where would the threads fit into that?
I guess the collection and then transfer of data and some one thread would actually make a decision on.
If you had a bunch of calculations that were independent of each other, you could break them up and have the threads perform calculations.
Right, so divide and conquer anywhere you could. Whenever your data is loosely coupled or not coupled at all, that would be a great place to come up with new threads.
I know that they used it, I think it was multiple processors, not so much threads, but it's the same idea where they were calculating the currents of planes and stuff. They were assigning each of the currents a unique thread, so to speak. So then they could make these wind tunnels that could actually project out what they were going to actually do with the aircraft.
Right, so in that case,
It
the
would be
the
more-
modeling for the aerodynamics.
Yeah, all around that, but then you can do the same thing like you said with the weather. You can take all the weather patterns and put them into individual threads and then kind of see how they interact with each other.
Certainly,
Another thing with threads is ray tracing, probably.
Yeah.
For rendering or
yeah,
whatever.
so in the old days, we had networks of Apollo computers and you'd creep onto other machines and spread your jobs out and ray trace a little bit at a time on different computers and then pull them together. Token rings, yeah.
Oh, yeah.
You probably never seen them and hopefully never will. I think you might see one in the computer museum in Boston, but that's about it. All right. Lots of different applications. Web server is a fairly common one. The web server is thousands of threads.
That's right.
A little bit on the front end, capture the data coming off the network. You could have multiple network ports for redundancy. All those requests get put in a queue. Then some more threads doing the pre-processing. For us that don't have a lot of patience and we're doing this, yeah, those all get dropped right away. Just it's like pushing the button in the elevator. It doesn't work unless you program it. But the big batch of threads are in the processing. So every request gets its own thread to do processing. They typically run them out of a thread pool. They don't even delete them when they're done. They just put them back in the list of threads to be used over. And then some transmit as well. In games, I think games are the obvious one now. All right. Threads versus processes. So why threads rather than processes? Already mentioned some of the pieces. Processes have lots of overhead. They have all the code, all the data, the heap, all that stuff. So when you swap a process in and out of memory, you get a lot of stuff to move around. Threads, on the other hand, they stay intact. They stay in memory because they're a part of the process that's in memory. And the CPU just does a context switch between those threads. So typically we get faster response. And we talked about that with the I/O. If a thread is blocked, the I/O still works. You don't have glitchy video and audio and so on. It's faster and easier to access shared resources. So shared resources meaning data and files and other things that are in memory. Threads can get to them because they're in the same process space. They're in the same address space. Whereas in a process, going from one or two processes sharing data, you have different mechanisms for doing that. You have things like mailboxes. You'll have things like sockets if you want to go real heavyweight. Resource economy, so less memory, certainly much less memory. Remember, there's one footprint of your code. How many of you have made a file, some application more than a megabyte, more than 2 megabytes? How big? Okay. So even if you had 100 threads in there, that size of executable doesn't change. That footprint that gets allocated in memory doesn't change for the 1,000 threads versus the single thread. And again, thread switching is much faster. You don't have to do a full context switch between threads like you do in the processor. And it's scalable. So if I take that program that's multi-threaded and I drop it on, say, the Intel Phi chip with 256 threads, it'll use them all. I don't have to go recode it. Where if I'm writing processes, multiple process systems, I will need to go and encode them to take advantage of more cores.
But the question, the threads up here, you were saying, are the threads, if you have a process, the process owns the threads. And if you have a time slice, doesn't when the process is time sliced out, the threads go out with it?
The threads go with it, yes.
So where you get the advantage is that when he comes back in, you can bring them in faster than you can the whole process. Or they have to come in after.
Well, they'll have to come in. They'll come in together. It's the same amount of time.
Okay,
The process with all its threads is the same amount of time.
but to get it up and going, once you get it back in the memory, it's quick.
It's quick.
Okay.
And then if your process has lots of threads, I'll move a second. If your process has lots of threads, maybe you push your quantum up higher and it spends more time resident and running
Okay.
because threads are doing different things.
Okay.
So Linux, the kernel itself is threaded, multi-threaded.
Okay.
So it can do a bunch of different things on your behalf. It doesn't have to do a full context swap for those pieces of process.
Okay, cool.
So with multiple processes running on a CPU with multiple cores, are some of those processes going to still be running simultaneously?
So that's up to the operating system and the hardware, if it'll allow multiple processes to be running on, say, 2 cores and a process with multiple threads running on the other cores. So the OS needs to be able to do that.
Do they? Like
There are some. I think the latest version of Solaris does that. Typically, you'll hear things like clustered systems, and which is a bank of computers that are run together. So typically, it's multi-CPU systems, not multi-core systems that are set up to run multiple processes simultaneously. It can be done. I mean, obviously, they're all virtually the same hardware.
Mhm.
So it's just a matter of doing it.
So like Windows or something wouldn't be doing that right now because the shared resources problem or something? Or-
Well, that certainly would be part of it. But if you look at Windows, if I pop up the task manager and you add up the total time spent by all the processes that are running, what does it add up to?
more than
100%, hopefully.
yeah, well, yeah.
But if all those were running separately, it would come out to, on 2 cores, 200%. So that's the really easy way to find out. Was there another hand that I saw pop up? Okay. All right. All right, let's talk a little bit about thread performance. More threads and cores are better, right? So far, so good? Well, adding more cores doesn't always give you lots more processing power. Amdahl's law, and you can notice everything is in the denominator, which is never good. That tends to make things smaller. This is no exception. So in this case, the speed up is less than or equal to this equation. Is this legible from the back of the room? Okay. So it's really based on the number of cores you've added, but S is the percentage of the code that's executed serially. So when you write your code, how much do you write serially and how much do you write that could be done in parallel? Or you don't really think about it so far. Are there things in your code that could be done in parallel? If you had a compiler that generated parallel threads, this is the 4th course in the series. So there's been some work to do threaded compilers. I think most of the work was done companies like Taliant way back, mostly for math processing, where the math was up there, scientific computing. So they look at large matrix operations and so on, and then figure out how can we pull these apart and parallelize them. All right, so let's just say we have some really efficient code and only 10% is serialized versus 80 or 90%, which is probably normal. 10% serialized, 90% parallelized. So an i7 with 2 cores and hyperthreading, your speed up is around 3%, 3x. And with the latest E7, that's one of the Xeon chips, 18 cores with hyperthreading, you get an 8x. So 36 cores, but only 8 times the performance. Is this less than what you'd expect? And why is that? What's limiting this?
It's really hard to parallelize a lot of tasks.
It's all about the software, right? So what's limiting this is you all have to go out and do it. Your next job. All right, just touch on some of the software that's out there for real applications. So pthreads, it's the POSIX interface. It's been around now, I think 20 years, maybe even 30, but it's the old IEEE standard. It's a C Unix library for thread programming. And there's really 3 different sets of instructions one for managing threads, creating and destroying them, joining, so you want your threads to join sometimes, versus running independent forever, or deattaching them. So maybe you want a thread to run off to the side and not be part of the process anymore. Mutex variables. So this is the mechanism I talked about for mutual exclusion. So when you have parts of your code in memory or data, and you don't want it to get corrupted by one thread or accessed by one thread while another thread is still writing it. So you'll put these mutexes around that, so you can lock down segments of memory, unlock them later. And condition variables are very similar. They're a synchronization mechanism. So you may have some data values, so more conditional, a little more powerful tool, but with the same idea that you can have variables or other pieces, other resources in memory that the threads are using to synchronize themselves or to share data with themselves. And I'm pretty sure that's an eye chart, so sorry about that. I don't know if I can make this bigger or not. Maybe I can. Yeah, oh, there we go. Not sure how to make one scroll bar go left and right as well as something else. So. All right, so in this case, the main program, I guess we should start there. Right on. Okay. So a P thread type, and in this case, I just put together 10 of them into a small array. I go off and I loop and I just create these 10 threads. So somewhere in the beginning of your program, you create the threads that you're going to use. In this case, I just print out what thread I'm creating and what my loop index is. So I create the threads. Now notice my thread function, third parameter in. We'll go take a look at that, and also the message. In this case, I've put together just a little text message. Okay, so the thread function in this case is a void star, which means anything you want it to be. And it just prints out what it's doing. So the way you would use this in an environment, you could start up and say, create your whatever number of threads you need, dozen or so threads. And then you just put together either a switch table so that each thread knew what it was, or you could just instantiate a function pointer to each of the specific functions and let them run as threads in the background. And if a thread ever crashed and burned, died, hung, got locked, whatever, you just delete it and reinstantiate it again. You wouldn't even have to restart the application or the process.
So it's a patch for bad coding.
Patch for bad code. No, not really. But it's certainly a way to increase the reliability.
Yeah.
And you could have a model where all your threads are doing the same thing, the web server model. So you just start up this pool, 1,000 threads per server. And each thread's just doing a couple things, getting a message about the next request, doing the processing, sending out the results.
Oh, I see. Yeah.
And then when that one's done, it can just say, I'm done. And
It's like if somebody's on the web and then they decide that they disappear and they're not there anymore, then it just drops it.
well, just per request, right? How many times do you click on the same link?
Yeah.
Or the same website? Maybe a couple of different times and you get bounced around
Yeah.
and go somewhere else. So
Sure.
that server's handling each of those requests in this fashion. Okay. Now, if your threads were very different, the code just has nothing to do with the code in one thread has nothing to do with the code in the other thread. You could have threads that are essentially hard coded. There's nothing wrong with that. In this little example, I join the threads together at the end. So I want all the threads to come together, finish what they're doing, and then I exit the main program. I could would leave them dangling. The main program would terminate, and then you'd see the threads terminate as the process exits and finishes. So a couple different ways to do this. Actually, lots of different ways to do this. All right. Let's kind of wrap up here. Just gave you a quick introduction to threads, an overview of processes, explored how threads are related to processes, what that relationship is, the parent-child. Discussed some applications, as did you, and examined the performance and why threads are not the one-all solution to computing. And then just a brief introduction to thread programming. Questions about threads? Just remember what your mother said about threads. Cut it, don't pull it. Thank you for your time, and sorry, can't stall you anymore. Good luck on your test.